chapter electrostats, what does it mean? It means charges at rest. Correct. Now, what is a charge? The first basic question that comes up in our mind, what is the charge? So charge is nothing but it's a intrinsic property of matter. So what do you mean by intrinsic property of matter? Intrinsic means anything which is independent of quantity of matter. Whether you take 1 gram of matter or very big quantity of matter, this property will always be there. It doesn't depend on the size or quantity of the matter. Okay. Now, how do we denote charge? By capital Q, sometimes small q also. Now, SI unit of charge is Coulomb. Types of charge, basically we have two types, positive and negative. Positive we generally denote like an example like a proton, negative for the electron. So basics, these all, since you have already done your PU or CBSE 12th, okay. So I'm understanding that you know the pretty basics. So I'm not going too deep down, students. Okay. Now it is a scalar quantity. So I think so you all know what is a scalar and a vector. Scalar quantities are those quantities which don't have what? Both direction and magnitude. So it just has magnitude, no direction. Now two like charges when you take, so since both are of the same nature, what will happen? If two selfish people, they accumulate at one place, they both will act selfishly, so they will repel each other. Nobody will like each other, correct? So if one is good, one is bad, okay, the good one will ignore the bad. So attraction can be there, and we know opposite attract, correct? So one positive, one negative, they attract each other, okay? Now what is the charge on a single electron? For one electron, if you see, that is equal to 1.6 into 10 power minus 19 coulomb of charge. So this much of charge an electron contains. Okay. Now, charges are additive in nature. So what do you mean by that? If I want to find the total charge for a body, let's say if I have a square body like this and I have a charge 9 coulomb, minus 3 coulomb, minus 100 coulomb, and let's say plus 20 coulomb, the total charge will be what? Just simple addition of all of them. Okay. So 9 coulomb minus 3 coulomb plus 20 minus 100. So we'll get minus 74 coulomb charge. Okay. Pretty simple. So basically total charge is what? Algebraic sum of all the charges. Let's see. Next concept is quantization. What do you mean by the quantization thing? Okay, quantization means that the charge always on a body is an integral multiple of E. So what do you mean by this? This word, the line sounds too complex, correct? No, it's not complex. What we are trying to say is whenever you find a charge on a body, it will be always in the integer numbers like 1 charge, 2 charge, 3 charge. It won't be like 1.5 charge. Okay, it won't be like 2.5. Let's say you go to the market and you say you want to buy bananas. Okay, you say I want to buy 2.5 bananas. Will they give you? No. So what do? You buy integral number of quantities, correct? So same thing here. The charges on any body will always be in the form of integral numbers. Means integers 1, 2, 3, not half, or what you say 1/3, 1/4 like that. So that is called quantization of charge, and that is equal to Q is equal to NE. The total charge is equal to integral number of electrons, the charge on one electron. Now let's see one question. We have to calculate the number of electrons in 1 coulomb of charge. So what we'll use? We'll use the quantization formula. What is the quantization formula? Q is equal to what? NE. Okay, so the total charge is equal to what? Number of electrons, charge carriers into the charge on each one of them, okay, or the charge on one electron. So total charge is given as what? 1 coulomb, and that is equal to number into the charge on one electron. So 1.6 into 10 power minus 19. So you send it that side. So N is equal to 1 by 1.6 into 10 power 19. So if you do the division, what will be 10 power 19 divided by 1.6? If you take this point out, 110 will come. So 10.20 by 16. If you solve it, you will get something like 6.25 into 10 power 18 electron. So what does it say, student? That in a charge of 1 coulomb or 1 coulomb charge contains some 6.25 into 10 power 18 electrons. Correct. So what they're trying to say, that 1 coulomb of charge is containing this many number of electrons. Okay. Now the next is charges always comes with mass. Okay. So whenever you have a charge, though how much small the what is the mass will be, mass always be associated with it. Okay, so means whenever we have a charged body, it will have maybe a bit less, maybe a bit more, but it will always have a mass. Now, is the vice versa also true? No. Okay, so do think on that. Let's see if you're able to ponder on that. If a mass body is having mass, is it definite? Is it sure like it will have a charge? Think on it. Put your answers on the comment section. Let's see how many people can, what do you say, understand and put this answer. Okay. Now, let's see the difference between charge and mass. So charge, very simple definition difference we can see. It can be positive, we already know, negative, and it can be zero. If the charge positive and negative both are same, so it will add up and it will come to zero, neutral. Now mass always positive. Have you heard of a negative mass? Never. Now charge is independent of velocity of the body. Let's say if a body has 1 coulomb charge, it starts moving. Let's say with a speed of 1 meter per second. Will the charge change? Illa. The charge won't change, correct? But if a body has a mass, let's say this is the body, a person, you are running, you started running at 10 meter per second. Now, the moment you have a velocity, what will happen? Your mass will also change, student, correct? So with the velocity, your mass will also increase. So what is the formula for that? That is equal to m is equal to m naught. M naught is the mass of the body when you are at rest. When you're not moving, that time what is your mass? That is known as rest mass. Divided by root under of 1 minus v square by c square. Now v is nothing but your velocity, okay, with which you are running, your velocity, and c is equal to speed of light. C is what? Speed of light. So we know c is much greater than v. So v by c will be what? Much less than 1. So 1 minus something which is very less than 1 will be a very big quantity. Correct. Again, understand. Very simple. Let's, what do you say, enhance it. What do you say? This value is much smaller in comparison to this c. So this whole value goes down because the denominator is what? Damn big. Okay. So due to this whole thing, so 1 minus something which is very small will be what? This will go up. Okay. So m is equal to m naught divided by something very small. What will happen? This will go up. Correct. So the moment your velocity increases, okay, so your mass also increases, student. Okay, charge is always conserved. So if you have an isolated system, charge, the amount of charge contained never changes. So what will happen? Charge you can't create, you can't destroy, but you can transfer from one body to another. You can transfer it. Okay, you can transfer, let's say, 10 electrons to some body. You can get it back. So you can do that. For mass conservation, yet we haven't, and mass is not conserved because why? We know Einstein's equation E is equal to mc square. But what will happen? The mass can be converted to energy and vice versa. Okay. Now, next is the force between charges can be attractive. If they are unlike charges, they'll attract. Correct. And if they're like charges, they will repel. But in case of mass, always they attract. Correct. There is no concept of what? Unlike or like. Masses always attract each other. Clear? So again, we are reading about the conservation. So conservation of charge, as I told you earlier, it can neither be created, we can't create a charge, neither we can destroy it. But yeah, we can definitely transfer, and for an isolated body, it always remains same. Clear? So very simple, we don't have much to do here. Okay. Now, for CD point of, what do you say, importance, Coulomb's law is very important. And among Coulomb's law, this epsilon plays a very vital role. So I've gone in length to explain this epsilon. A lot of people, they mug up the formula and they don't know what is the meaning, okay, or the physical significance of epsilon, and they just mug it up, okay, the values and all. So few times it helps, like if a value based question is coming, you'll be able to solve. The moment a concept based question comes, and you will be able to, you can, if you had understood, if you had known the concept properly and thoroughly, you would have solved the question in less than what, 5 seconds. But since you don't know the concept, you won't be able to solve it. So understand the concept here. Very important. Okay. Now, so what does this Coulomb's law says? So Coulomb, sir, what he found out is two charges, if you have one is Q1, one is Q2, they attract each other or they repel each other, which is directly proportional to the force that they exert is equal to the product of the charges and is inversely proportional to the square of the distance between them. Okay, so you found out two things, that the force between two charges is directly proportional to what? Their product, and the force is inversely proportional to the square of distance between them. So we'll learn more in details about these two. What do we mean by that? Let's understand few more stuff. So let's say this is a positive charge. This is again positive. So what will happen? Two like charges, so they'll repel. So the first charge, what does this F12 force means? Means that force on the first charge due to the second. The second charge, see here, it is repelling this one. So how much force, with what force it is repelling? That is given by F12. And since it's a vector quantity, so that's why direction is also there. So F12 means what? The force on the second charge due to the first one. So similarly, if you have F12, what about F21? The force on the what second charge due to the first, because the first will also repel the second one, correct? Now, second point is what we have to know is force always acts along the line joining. Okay, so if this is one charge, this is one charge, force will always act between the line joining. Okay, these two charges. Okay, that's why it is also known as central force. Okay, clear? Or it is central in nature. What is the force formula? F is equal to, we got K, we removed the, what do you say, proportionality, and we got F is equal to K, Q1, Q2 by R square. Now, if I remove, what is the value of K? K is nothing but 1 by 4 pi epsilon naught. Now, what is the value of this, student? The value of this for numerical part we'll be using is 9 into 10 power 9 Newton meter square per Coulomb square. How to get this, what is it, unit? Very simple. F is equal to K Q1, Q2 by R square. So you already know the unit of these two, correct? Coulomb square. This unit is what? Meter square. And you already know the unit of force, correct? So done. Once you substitute it, you will get the unit of what? K, or 1 by 4 pi epsilon naught. Now, what is the value of epsilon naught, students? That is equal to 8.854 into 10 power minus 12 Newton inverse meter inverse Coulomb square. Clear? Okay. Now, next important thing, what KCET basically asks you is inverse square law. What do you mean by this word inverse square law? Correct. A very simple word, but sometimes we don't understand. So inverse means what, student? Like if something is inversely proportional to other means what? If one increases, the other has to decrease. Correct. We have read a lot of times, we have heard in economics and all that, that when supply increases a lot, the demand decreases. So what it means, when the quantity of products available in the market increases, the demand of that product decreases. Or in terms of, what do you say, physics, if you want to say here, what is happening is the moment you are increasing the distance between these two charges, okay, the moment you are increasing this distance r, so what is happening, the force is going down, correct? So the moment they are far away, we see, whenever some of our friends, they go very far from us, so we say that, yeah, now the bond will be like weakened, the force of attraction that we had will become, what is it, very less, correct? So same thing, the inverse square law also says the same thing for the charge. If you have two charged particles, let's say these two, one positive and negative, they're attracting each other. So the moment you increase the distance, okay, so what will happen? This attraction force decreases. The moment these two charges go far, so what will happen? This attraction force will go down. Clear? So that means inverse square law. So inverse means one increases, the other decreases. If one increases, the other decreases. And square means what? So how rapidly it is decreasing? Square of this. Okay. So if you want to plot a graph, a lot of times graphs are also very important. So we see that if the force here is maximum, the R, the distance is minimum. The moment we increase the distance to max, the force becomes minimum. So very important, students, okay. And this inverse square will be able to solve a lot of questions based on this in the PYQ section. The moment we'll upload the questions on the PYQ, you'll be able to understand a lot of the questions will be directly based on this part, okay? Inverse square law. So again, understand inverse means what? If one increases, the other decreases. Now, and square means how faster it is happening. So square of this, it is happening, okay? Now, so let's see one simple question. If R becomes doubled, so how fast the force will be, or how much will be the force decrease? So F is directly proportional to 1 by R square, we know. So if R might becomes, let's F dash will be what, 2R square? Because now the distance became double. So what you'll see, F dash will be equal to what? We'll see 1 by 4 times of R square. So 1 by 4 times the new force decreases by 1/4. Okay. So if R became double, the force became what? 1/4, student, 1/4. Okay. Clear? No. So sometimes a lot of question you'll get like, what do you say, force is there, normal case scenario, R distance. Now what you have done, you have made the distance 3R, you got a new force. What is the ratio between these two? So in that case, directly what you can do, F directly proportional to 1 by R square and F dash directly proportional to 1 by 9R square. So you can solve it and you can get the answer, okay? So these types of questions you will be able to solve in just seconds, okay? So you need to understand how to use these concepts in the numerical part and how you can make it more faster. Okay. Now validity of Coulomb's law. Till where and how much is the Coulomb's law valid? So we need to understand where to apply Coulomb's law. We know Coulomb's law is there, but where we can apply, where we can't. Now, whenever we have a extended charge, means a very big charge, okay, extended out. So in that case scenario, we can't. Because Coulomb's law we can apply only for point charges. Now, second thing is, if two charges are at rest, let's say this is your charge Q1, this is the charge Q2, and the both are at rest. So this is also rest, this is also rest. Now we can apply Coulomb's law. Okay, we can get the force. Now, what if the both are in motion? One charge is there, positive, started running 300 meter per second. Negative also started running 20 meter per second. So can we apply? Illa. We can't apply here. If one charge is at rest and the other charge is in motion, can we apply? Yes, we can apply, students. Okay. So understand the validity where we can apply. First thing, very simple. If it is two big charges, okay, so or two extended charges, not a point charge, not kind of big, you can say, like an extended body. Okay. So in that case scenario, we won't be able to apply properly. And the second case is if two charges are in motion, then we won't be able to apply it. Okay. So very important, the permittivity. Now permittivity, a lot of students you have heard, sir, epsilon naught is nothing but permittivity of free space. So what do you mean by this permittivity of free space? Okay, permittivity by the word permit means what? To allow, correct? To allow something. But actually here in this formula or in the definition of permittivity of free space, what do you mean by that? Let's see. So we know F is equal to the force is equal to what? K Q1 Q2 by R square. Correct. So we can, this is the Coulomb's force, we know. And we know K is what, student? K depends on the medium. What kind of medium we are taking, it depends on that. How we'll see in a bit, what do you say? In one or two, what do you say? Later we'll see, just now we'll see. Okay, don't worry. So K is equal to, we already know the formula, 1 by 4 pi epsilon naught. So force already we know is equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. So we have already put, now see, force and epsilon naught, they're what? Indirectly proportional. Correct. So if epsilon naught increases, this has to decrease. Correct. So they are inversely proportional. So that one thing we know. Now dimension also we can find it out. If we can find the unit, we can find simply the dimension. Now what do you mean by epsilon naught is, understand, let's say, take a simple example relatable to your, what is it, general life, okay, to your day-to-day life. Let's say this is your friend A and this is another friend B. Okay, two friends are there and they were having a very great conversation. Okay, and they were talking about what? what is going out in house, like, or what games, or about a recent FIFA match. Okay, they're talking about, and they were really very engaged in that topic. A certain person C came, okay, and this person is very irritating person. He started interrupting, correct? So what will happen? This whole conversation will be interrupted. This the whole attraction, the force which was happening here will be interrupted by this C person, correct? So now we'll understand by this theory how this C person is disturbing, okay, and what is this. So understanding the charge concept, let's say we had one charge Q1, another charge Q2. So they were having a very good story, a very good force and all everything. Now the medium came epsilon. Here let's understand epsilon naught. Okay, so maybe vacuum. Here in the case, let's say for the vacuum part, it came and it made its own field. What to do? To disturb this bond, okay, or to disturb the force or the interaction between these two charges. Okay, so how strong it can make its own field to disturb them, what will happen? Their understanding, their conversation will be disturbed, okay, depending on how, what to say, irritable the person sees, okay. So let's again see it. So person A, person B, they were having a very great conversation, and person C came in between. Now, this person has a tendency to irritate people a lot. So, what it will do, it will, what do you say, make these two people, like, what do you say, their conversation go almost nil because this person is very strong, correct? Now let's say we bring one more person D here. Now this person, he irritates, okay, but to a very limited part. Okay, so what will happen? This time the conversation will go on, but a bit slightly it will be disturbed, correct? So this is our person D, which is disturbing the conversation, but very slightly. So what it is doing is it is creating its own aura to disturb. So basically epsilon for free, epsilon naught for free space means what? That the free space of the air, here vacuum and air, we take it same thing only. So the air is creating its own field to disturb the charges which were interacting. Okay, so the more strong the field is there, okay, the more it will disturb. Okay, we can understand one way like this. What about other way? Let's see. So the property of the free space which allows its own field to decrease or disturb, okay, the interaction between charges. Okay, so the more stronger the field, since air we can understand the particle, the medium is very weak, so it doesn't disturb much. So that's why we can understand the force in air is what? Maximum, correct? The force in air is equal to what? Maximum. Why? Because the epsilon naught or the medium here is minimum. The medium disturbing tendency is what? Minimum, correct? The medium is not able to disturb because it is not that strong, correct? The person D which is coming, it is not that irritating. So it is not able to irritate the whole conversation between A and B. Okay. Now, so basically epsilon means what? This epsilon, okay, or the permittivity, it creates its own field. What to do? To do what? To disturb the interaction between the charges. The more stronger it creates, the more it will disturb. The more weaker it is, the less it will disturb. Okay, so the capacity or the property of a what do you say medium to create or to allow its own field, what do you say, to disturb or what do you say, decrease the interaction, that is known as epsilon naught. So less the epsilon naught, more will be the force. And the force concept. Let's say you have a medium. So force between a medium is what? 1 by 4 pi epsilon. Okay, this is for the medium, or m you can write. Q1, Q2 by R square. Now what is happening in a medium is there two charges where there, let's say Q1 and Q2, they're having a very great bond, very great interaction. And the medium, what it did is it created its own field to disturb them. Now, since the field created by the medium was strong, so these two forces got disturbed, and the force in the medium for these two charges got reduced. Correct. Now, in the vacuum, what happened? Here again, the vacuum also tried. Then this Q1 and Q2, they were having a very good, what is it, interaction. Vacuum also tried to disturb them. But since the vacuum was not that strong, it was not able to create a very strong field to disturb them. So what will happen? The force in the vacuum part will be what? Very, very strong. Okay, it's almost to the max. Clear? So understand the concept. Epsilon is nothing but property of the material to allow its own field to disturb or decrease the force between charge. Okay, so more stronger the material, more stronger it will allow its own field to disturb the charges, and the weaker will be the force. So inversely proportional, student. Okay, the more what do you say, strong epsilon we have, or the medium we have, the more it will tend to disturb the force between charges. Okay, now what is relative permittivity? Now relative density, we know relative means what? With respect to something. So the relative permittivity means what? The permittivity of a medium with respect to air or vacuum. So we say with respect to vacuum, how strong you are. Correct. So whenever our parents, they do a, what do you say, comparison. They say the son of Sharma ji is so good. You're like one third of him, or you're like half. You're not studying half of that. Correct. The amount what Sharma's son study, you just study half of that. Correct. So our parents used to do the, what is a comparison. Same thing here in the relative permittivity. We also do the comparison, and we compare with a standard. What is that? Epsilon naught, the permittivity in the free space of vacuum. How strong is the allowance or permittivity of a material with respect to what? The air or vacuum. Okay, so we'll see that. Now permittivity in space is what? One. So almost whatever is your interaction, it allows that. Okay, it doesn't disturb. And for any medium, it is always greater than one. So the moment this is greater than one, force will be less because it will disturb. It is inversely proportional. If this goes up, the force will go down, student. Okay, and we always know that the epsilon of the medium is always stronger than the epsilon naught of the what? Vacuum. Okay. Now, so epsilon m, permittivity of the medium, is nothing but epsilon relative permittivity into epsilon naught. Now, what do you mean by this? Let's understand with a simple question. They have given us the relative permittivity of a medium is 100. Okay, so it means that permittivity of the medium by permittivity of vacuum is equal to 100. So permittivity of the medium is 100 times of the permittivity of the vacuum. So how much times it is with respect to vacuum? It is basically given by epsilon r, if you know that. So if somebody is saying that the permittivity of, let's say, water is this much, so we means that the, what do you say, whatever value, let's say the permittivity of water is, let's say a rough value is 7. So it means that 7 times it is more stronger than the permittivity of vacuum. Okay. Now, a very important part, permittivity of a conductor is infinity. Now, how and why, student? You need to think. Okay, I'll just give you a small hint. We know the electric field inside, we haven't talked about the electric field, but still I'm giving you, since you have already done your PU, inside of a conductor is 0. So what will be the force? What will be the permittivity? Think about that. For air and vacuum, we already know it is 1, and for any other medium, it is greater than 1. Okay. Now we'll study the principle of superposition. Now what this principle of superposition is, we need to understand. So first, if we see, if we had one charge Q1 and the other charge Q2, so it was very easy to find the force between them. What was the formula? Force is equal to K Q1 Q2 by R square. Now what if we have more than two charges? Let's say we have a charge Q1, we have a charge Q2, we have a charge Q3, we have a charge Q4, and we have a charge Q5. So according to the principle of superposition, what does it say? That the net force on any charge is equal to what? A vector sum of all the forces acting on the charge. Means if you want to find the F net or total force, what do you do? Just vector form, you add up all the forces. Vector form, you add up all the forces. Why we are saying vector form? Because it helps us in deciding the directions. Okay. So which one will be cancelled, which one, like one force is like this and the other force is like this. If both are of the same magnitude, so what will happen? This is F1, this is F2. If I add it vectorially, what will happen? They'll give me 0. Okay, so you need to understand here. Okay. And the second part, what we got from principle of superposition is the individual force between two charge. Let's say I'm finding Q1 and Q2, the force between these two. Okay. It doesn't get hampered by any other charge like Q3, Q4. Presence of these charge doesn't hamper the force between these two. Okay. So 2 points we learned here. First, the net force is nothing but algebraic sum of all the forces. Okay. So what you do is, instead of, like in reality, what happens is, if a problem comes in our life, so what happens? It doesn't come just like one problem. It comes second, third, we have like four problems. Okay. So the total problem is what? The summation of all the problems. Correct. So in the same case scenario, okay, in charges also, the net force, what you want to calculate on Q1 is equal to the force on first charge Q1 due to Q2, the force on Q1 due to Q3, and the force on Q4, what is it? The force on Q1 due to Q4, and the force on Q1 due to Q5. Means it is nothing but the vector sum of all the forces on Q1 due to Q2, Q3, Q4, and Q5. The same way what he told is like the problems, okay, the total problem that we are facing, or a person is facing, is equal to what? What problem we got first, the second, the third, the fourth. Okay, so the total problems will be all addition of all these problems. So here in problem that is not a vector quantity, so we don't do, what do you say, vector addition of that, but the forces here are vectors. Okay, so we do vector addition of that. Okay. Now we'll talk about the concept of electric field. What is electric field? Let's see the basic definition about it. Okay. Space around a charge in which another charge, or a test charge basically, experiences the electrostatic force of attraction or repulsion. Okay. So very, what is it? This is the definition. What in simple terms, what is the feel of it? How do you get the feel of it? So basically, let's say you have put up a charge Q and you're bringing some test charge Q naught here. The moment you're bringing it closer, closer from whatever direction you're bringing, suddenly you'll see that it is starting getting repelled, because both are of like what? Like charges. So it starts getting repelled. So this, what happened? Why is my this test charge getting repelled? It means that due to this charge, some field is there, and the moment it is coming inside that field, it is getting what? A force, or getting pushed away. Okay. So that is basically the concept of electric field. Now if you say I'm bringing a test charge and I'm getting a force, okay, and but I'm not able to see the charge. So it means what? The charge is here. Whether we see it or we don't see it, its effect we can feel it. Correct. So it means that the space around a charge in which its effect we can feel it, okay, whether we are able to see or not, if we are able to feel that effect, means that is the electric field of that charge. Till that position or till that space, the electric field of that charge is there. That's why we are able to experience that force. Okay. So if you're bringing for a positive charge, we know the electric field lines are how much? Outward. Why? Because whenever you bring a test charge, and we always bring a test charge, which is like almost of 1 unit, okay, and which is very, very, very small, like a very small thing, so that this doesn't disturb this charge. And the moment it comes, it gets a force outward, because positive, positive, they'll repel each other. So that's why the electric field for a positive charge is radially outward. The reason for radially outward is what? When you bring a positive charge, already a positive charge is there at the center. So what it will do? It will push it outside. Correct. So that's why for each point, whether from whichever direction you bring it, okay, the force will be what? Radially outward. So for a positive charge, this is like the electric field. Okay, radially outward. So I don't think so. Now you'll have any doubt in this. So again, now the definition will sound pretty clear. Space around a charge means space around a charge in which another charge, when let's say here you are bringing up what you say Q naught, in which another charge can experience an electrostatic force of attraction or repulsion. In this case, it is facing what is repulsion, because like charges, if it was unlike, you could have faced an attraction also. Okay. Electric field can also be defined as force by charge. That is basically test charge. So if you can say it is electric field is nothing but the force per unit test charge. So that also we can do the definition, okay? Now coming to the next part, what we have for a negative charge, what will happen? So same thing will bring a positive test charge. Okay, so what will do? This negative charge will attract. So it is radially inward, correct? It is attracting from outside, from all sides, correct? So it is radially inward. So for a negative charge, the electric, what you say, field lines are radially inward. Okay, this will just cut it. Okay, it will be inward. Now, what is the value of electric field or electric field intensity or electric field strength? These are the different names we have given. Now, the moment we know that there is a field, but we want to know how much it is. Okay, what is the quantity of it? Will it be able to, what do you say, uh, will it be able to repel a very strong charge or a weak charge or just a test charge, and by how much? So in order to know that, we need to know the strength of the electric field. Okay, and in order to do that, what is the formula? We have a definition. What is that? Electric field strength or electric field intensity is nothing but electric field is equal to force by charge, where charge is almost tending to zero. Now it is the vector quantity, student, okay, and the unit is Newton per coulomb or volt per meter. Now this unit volt per meter will be discussing in the next page, okay. Now electric field will also read a definition in the next chapter, that electric field is equal to potential by potential gradient, okay. So potential by distance, so that is equal to, we can use volt by meter, okay. So we can use this definition also. Now we know electric field is equal to what? Force by charge. So that is equal to what? We'll put the value of force, Q by R square divided by Q. So this Q and this Q will be cancelled. So we'll get K capital Q. This is the source charge which is producing the field by R square. So what we see here, again we have the inverse square law. So the more far away we are going from a point which is producing, what do you say, the electric field, more far we are, the less will be the electric field. Clear? So it is inversely proportional to the square of the distance between the point and the charge. Here also, in this case, you can use superposition principle. If you have more than one charges, then the net electric field will be a vector sum of all the individual electric fields. Clear till here? Any doubt? You can ping us in the WhatsApp group. Link is in the description. You can also, write a mail to us. You can also put up, whatever the difficulty you're facing in our website, and you can also ping in the comment section, okay. Next is electric field lines. Now the word, what do you mean by electric field lines? So what we read is, it is imaginary, either straight or curved lines in which the tangent gives the direction of electric field. Now, the moment you say imaginary, because see, the moment we have a charge, we don't see the lines in reality coming out of it, correct? That's a concept that we have made to understand, okay? So these all lines are, they don't exist in reality. So that's why they are what? Imaginary. So they can be either a bit curved like this, and the tangent at this point will give me the direction, or they can be straight also. Both we have, okay? So what are electric field lines? These are imaginary straight or curved lines in which if we draw a tangent, they'll give me the direction of electric field. Okay. Now what are the properties? First, they start from positive charge and end up in negative. That is one. They never intersect. Why? If they intersect at one point, we'll have what? The two direction of electric field, which is possible? Not possible. Illa. Correct. Now electric field lines do not have any breaks. They don't break, like half it go on and then again like break as this. This is not there. Okay. Because they are continuous in nature. They're what? Continuous in nature. Next is flux. So flux concept is pretty simple, student. Flux is nothing but the number of field lines. Now since we said these are imaginary lines are there, so how many numbers are passing perpendicular to the surface? Let's say I have a surface like this, okay? So how many of the lines, field lines, are passing perpendicular to this surface? Okay, that gives me the flux. So flux is equal to phi is equal to what? E dot delta S. Okay, clear? So very simple concept of flux is we wanted to know the number of field lines. So we can say in this much area, this much perpendicular lines are there. So that basically gives us the electric flux. Next, what we have a concept is of dipole. What is basically a dipole is, it's a very simple concept. We have a positive charge, we have a negative charge, and we have separated it by a small distance of 2L. Now that creates the whole system of a dipole. Okay, equal and opposite charge separated by a small distance of either 2A or 2L, whatever it is, that is correct. Now, what is the direction of dipole? Always the dipole is from negative to the positive, from negative charge to the positive. So this is the direction of the dipole. Very important, students, for the KCET part, especially very, very, very important. Okay. So always remember, dipole direction is what? From the negative, it is going towards the positive. Okay. Now, dipole moment. Okay. Dipole moment is basically the measure of the strength of the dipole. So basically dipole moment we denote it by P, and that is equal to any of the charge because both of same into distance between them. So Q into 12. So product of either charge and the distance between them. That is known as dipole moment, and that is the value of dipole moment. So this is the last part of the chapter, electric charges and fields. So basically in this part, we'll be studying about the different formulas, what are very important and very crucial for the KCET. Now the derivations we haven't done because we are not studying for PU or the CBSE boards. So derivations I have removed. Only the formulas and the stuff which is important I have kept it here. Okay. Though I have written a bit here and there, but the most importance and focus should be given on the formulas part and split small places where you need to know a bit stuff which KCET asks. Okay, so let's see. Now, electric charge is due to a dipole. So we already studied what is a dipole. Now we're trying to study what is the electric field produced by a dipole setup. So basically a dipole setup, as we can recall, is nothing but two equal and opposite charges separated by a small distance. Okay. Now, what is the dipole, electric field due to a dipole? We want to study. Now, first on that is at an axial position. The moment we listen to this word axial, what does it comes to the mind? What does it ring a bell? Okay. What does the word axial comes? Okay. So basically what does the axial line means is if you're taking a positive charge, okay, if you're taking a positive charge and a negative charge, the line joining the positive and the negative, any point lying on this line, let's say here, any point lying on this line is known as what is a point on the axial line, or this line is known as the axial line. Okay, so this is very important. So here in this case we are trying to find the electric field at point here. Okay, let's name it as P. At point P we want to find the electric field. Now we know due to this plus Q charge, okay, what will be the electric field? This side, it will push a positive charge here, it will push it this side, and this minus Q will attract it this side, correct? So the net electric field is equal to what? E of positive minus E of negative charge, correct? Now, we already know the electric field formula, that is equal to what? KQ by R square. So that is equal to 1 by 4 pi epsilon naught Q by here. What is the distance? Now the distance what we take is for the positive charge, it is how much? This total is R distance from the center we are measuring, student. Very important. And this is L from the center. So this part will be what? R minus L, correct? Pretty simple. So it will be R minus L the whole square. And if you see this part is L and this part is R. So for the E of minus Q, electric field will be 1 by 4 pi epsilon naught Q by R plus L whole square. Okay. Once we got this, we'll substitute in the formula and directly this part of the formula we need to mug it up. Okay. That is equal to E net is equal to 2 PR by 4 pi epsilon naught R square minus L square. Okay. Now what is this P? P is nothing but dipole moment, that is equal to charge into the length. Okay. So this is important. Okay. Now what we have to understand in this is E and P both are in the same direction. We know the direction of the dipole is what? From negative charge to the positive charge. Here also the same thing. The direction of the net dipole is from the same direction as that of the dipole moment. Okay, so P and E are on same direction. This concept we'll be using and we'll be solving a lot of KCT problems. Okay, now there is again a small concept of short dipole. What is a short dipole? If this R length becomes much greater than this dipole length, so what will happen? We can neglect the L square. So in that case scenario, what will be the formula? Electric field is equal to 2p by 4 pi epsilon naught R cube. Okay, so these two formulas are very important, students. Okay, so coming to the next is the equatorial. Now again we need to understand what is an equatorial line. We need to understand what is an equatorial line. Pretty simple. The line which is perpendicular to the axial. Okay, so this is my axial line. So the line which is perpendicular to the axial and passing through the center of the dipole. So two conditions. First, the axial line. This line should be perpendicular and it should pass through the center. So basically what is it? It is just the perpendicular bisector of the axial line. Okay. So my voice got a bit, by shooting a lot of videos, it's got a bit cracked. So do bear it with. Okay. So I'll try to put up all the videos. Okay. A bit on the sound part. We are trying to work hard. Okay. So let's see. Now this charge minus Q, it's trying to pull this, towards itself. And this one is trying to push it. So by vector algebra, if you want the resultant will be somewhere in between. Now this, if somebody doesn't know, do we'll be putting up the lecture on vectors also. Do watch it out how we are getting the resultant E net here. Now the direction of E net is what? Towards the left hand side. But if you see, the direction of the dipole is what? From negative to positive. So the direction of dipole moment is like this and the direction of electric field is like this. So one very important point which you need to keep in mind is this one. The direction in equatorial case is what? Opposite. So electric field and the dipole moment, they are off in opposite direction. And the formula is 4 pi epsilon naught R square plus L square whole power 3 by 2. Okay. Now for a short dipole, you can neglect the 2L part. Okay. And then you'll get this formula P dipole moment divided by 4 pi epsilon naught R cube. Okay. So important thing is this part, very important. The direction, because the electric field direction is like this. Dipole direction is like this. Okay. So opposite direction means 180-degree direction. Okay. And that's it. And this formula. Okay. Now let's see the next page. Now what is the relation that comes up with axial and equatorial? So very simple. With this relation also, a lot of KCET questions will be solved. Your electric field at the axial is double that of equatorial. So axial is always greater than the equatorial. Okay. Now this part is not there for KCET still. We have put up in case, very rare chances if it comes up. You should know at an angle theta, what will be the value? Electric field is equal to 1 by 4 pi epsilon naught P by R cube. Okay. Root under of 3 cos square theta plus 1. Now if I put theta is equal to 0 degree or 180 degree, we'll get the axial one. And if I put theta is equal to 90 degree, we'll get the condition of equatorial. Okay. Now dipole in a uniform external field. Now what we had is, we had a dipole and we kept in a external field. Okay. So what will happen? Due to this field, force will act on this plus Q charge, it will be towards the left, towards the right. And on this minus Q charge, it will be towards the left. So what it will do, it won't move it, but it will try to rotate it. So the moment rotation force comes, okay, so a torque comes, a rotating force comes means a couple or a torque comes. Okay. So let's say like a hinge, you're pulling one thing like this and with the same force you're pulling like this. What will happen? From the center of this point, it will start rotating, correct? So same thing happens. Now, don't get very much confused and too much, don't get very much confused and too much scared by this. Torque, understand it's simple as a force, but it is rotating in nature. It doesn't make it move. It just makes it rotate. Okay. Now about the axis from the center. Okay. Now what is the formula of torque? Torque is nothing but either force. Both the forces are same. So any of the force you take, into perpendicular distance between them, into this perpendicular distance between them. So I've taken this force, and the perpendicular distance between them is this one. So force formula is what? F is equal to what? Charge into electric field QE, and this distance is what? 12 sine theta, because this was 12, this is theta. If I want to use trigger, it will be what? 12 sine theta. Correct. So force is equal to QE into 12 sine theta. So charge into 12, I know that is equal to P and E sine theta. So P and E sine theta, I can write it as P cross E. We already know A vector cross B vector is what? AB sine theta. Clear? Done. Now this part is also very important for KCET. Okay, so mug it up, very important. If theta is 0, then torque is also 0 and the condition is stable. So it is in stable equilibrium. Theta 90, torque is max, unstable. Theta 0, what is it? Theta 180, this is not unstable, neither stable nor unstable. Okay, theta 180 degree, so torque will be 0, unstable equilibrium. So very important to understand what is stable, unstable. Let me show you with a small diagram. Okay, so let's say you have a bowl like this. You put a ball here. Now if you displace this either left side or right side, after the force you have removed the force, what will happen? It will come back to original. So that is known as stable. Stable means where the particles, once the external force is removed, it tries to come back to its original. Now next we have a neutral equilibrium. So this is a straight, what do you say, table, and you have kept a ball here. So the moment you displace like this, after walking some distance, after covering some distance, it will stop. So it will attain a new equilibrium. So that is known as neutral. Now, what is unstable? Like let's say we have a bowl like this and you have kept something like this. So the moment you push up or you give an external force, it will start going down and it won't be able to come back to its equilibrium. So that is known as unstable. Okay. Now, the other important point, what we have to keep in mind is dipole in non-uniform electric field. What happens? The net force will never be zero, but the torque may or may not be zero depending on the orientation, how you're keeping it. Okay. So net force, translational force will never be zero if it is a non-uniform electric field. Okay. If the fields are like this, non-uniform electric field, in that case, the net force will not be zero, but the torque may be or may not be. Both the conditions are there. Okay. Now next, work done. So since we have force, we have angular displacement, means a body is getting displaced by some angle. Let's say it was here initially I1 position. Now it got displaced by I2. So it is doing some work done. So what is that work done? P sine theta d theta. Okay, torque we already got P sine theta and d theta. Integrated, you will get work done is equal to P cos theta 1 minus cos theta 2. And this work done is also stored in the form of potential energy. Okay. Now next is area vector. Now area vector is very simple to visualize for any kind of thing. What is area vector? Outward normal. The normal or the perpendicular which is coming outside. Okay. So what is area vector here? Outward normal, always keep it in mind. Okay. For any kind of diagram. Let's say we have a cylinder. For this face, what is the outward normal coming out this side? For this face, this side. Correct. For this part, outward normal is up. Okay. Same. So flux is nothing but number of field lines, and that is equal to E dot A or EA cos theta. Okay. The unit of flux is what? Newton meter square per coulomb. Next is Gauss law. So our Gauss said very, what is a simple thing and a very good thing. What he said is the total flux through any closed surface. Let's say one closed surface is there. You want to know what is flux? Number of field lines coming out of it. So the number of field lines that is coming out of this closed surface is nothing but how much charge is there divided by epsilon naught. So what is it? The total flux through any closed surface is equal to what? E dot ds, and that is equal to what? Charge contained inside that by epsilon naught. Correct? Very simple. Okay. So let's say for this part, if I want to know what is the total flux, what I'm going to do? I need to find what is the total charge. So if I see 2q positive charge, 2q negative, what is the net charge? 0. So charge enclosed is 0. So flux will also be 0. That's simple. Okay. So Gauss law states that the electric flux through any closed surface, electric flux means what? The number of field lines which are coming out of the surface. Okay, normally. So the field lines, okay, how much are their number? That is equal to, that can be given by the charge enclosed means how much charge is there inside the surface divided by epsilon naught. So the flux is nothing but equal to charge enclosed by epsilon naught. Okay. Now, applications of Gauss law here, you need to just know the formula, just given it up, that if you want to find the electric field due to an infinitely long straight wire, now the derivations are there for the PU. For KCET, we are not doing the derivations. Directly, the formula is electric field is lambda by 2 pi epsilon naught r. Now, a lot of students will ask, sir, what is this lambda, sir? Lambda is nothing but charge by length. Okay, lambda is known as linear charge density. That is how much charge is there per unit length. Like in 1 meter of length, how much is the charge? So you can get per unit of length, how much is the charge that is given by lambda. Okay. Coming to electric field due to a thin infinite plane sheet of charge. Electric field due to a thin infinite plane sheet of charge. So we have a plane sheet of charge. So due to this, what is the electric field is? That is equal to sigma by 2 epsilon naught. Sigma by 2 epsilon naught. What is the sigma again? This is surface charge density. How much charge is there per unit area? Lambda was linear charge density, charge by length. Now for the spherical shell, we know what happens. Charges stay outside. Okay. So when we are doing for R greater than capital R, so my Gaussian surface is taking up all the charge. Okay. The charge enclosed is what? Capital Q. So 1 by 4 pi epsilon naught by QR square. Correct. Now here also same thing when you are talking about outside one. So it is the same formula. Now it's basically similar to point charge. When it is at the surface, again same thing. Electric field will be is equal to Q by 4 pi epsilon naught R square. Okay, because Gaussian surface here also same. Now here this one is very important and this one. When you're taking it inside, what will happen? When you're taking it inside, what will happen? No charge is there inside. So electric field will be what? Zero. Because electric flux will be what? Charge enclosed. So charge enclosed by epsilon naught. So this is equal to zero. So electric field is equal to what? Flux is equal to E dot dA. Correct. So electric field will also be zero because no charges contained inside. Now, for R less than R, here charges are there. So we have to find for this much small r, how much charges are there. So that's the formula is 1 by 4 pi epsilon naught QR by capital R square. Okay, that is this much. So that sums up. The last part is the diagram, the graph. For less than R, it's zero. Again, it starts from the top and starts decreasing as we move forward. Okay, the more and more distance increases. It starts from see, in this case, what happens inside also charges are there. The more bigger circles, more charge it will contain. So it goes up to the max for the circumference R, and then the more you go outside, it will contain same charge, but the distance is increasing. So that's why electric field goes down. Okay, that's it, student.